Welcome to this video where we'll see sliding window protocols today. First, we'll see the 1-bit sliding window protocol, wherein we'll see what is called as the sliding window first. Then we'll see the multi-bit sliding window protocols, for example, go back N protocol, and lastly, the selective repeat protocol. The simplex protocols that you have seen so far are inherently, as the name indicates, simplex. That means they transmit the data only in one direction. Now, to make the communication full duplex, one strategy is to run the two instances of one of the previous protocols, where one will be a forward channel and the other will be the reverse channel. So there'll be separate data link for a simplex data traffic in different directions, means both the directions. But the better idea is to use the same channel in both the directions, where the data frames between A and B will be intermixed with the acknowledgement frames between them. And the difference between the data and the acknowledgement frames will be told by a kind field that sits in the header of the incoming frame. Now there can be one more improvement that is called as piggybacking, wherein we will be able to send the acknowledgement frame together with the new data frame. That means there is no need for a separate acknowledgement. The data frame being transmitted can have the acknowledgement embedded in it. Thus, piggybacking is the technique of delaying the acknowledgement for a bit to be added to the next outgoing packet. So the advantage obviously will be the utilization of bandwidth. For example, the data frame itself is being utilized for acknowledgement. So there can be multiple data frames at the same time, or there can be there is not need of separate acknowledgement frame, thus giving the same bandwidth for data transmission. Secondly, as the number of frames, the acknowledgement frames separately are not needed, correspondingly the number of frames will be decreasing and less processing is there. But this technique adds another complication. For example, if the data frame where which is to be piggybacked with the acknowledgement, that data frame has to be available within a short time period, that is particularly less than some milliseconds. If it is available, it can be used for piggybacking. If it is not available this way, receiver needs to send a separate acknowledgement frame. Now we'll know what is called as a sliding window. At any instant of time, the sender maintains a set of sequence numbers that correspond to frames that are permitted to be sent. What does it mean? For example, let us say the sender is allowed to send 3 frames. Now there will be sequence numbers corresponding to those 3 frames. And once those 3 frames have been sent, the sender can then move on to send next 3 frames. So those frames are set to fall within a sending window, which frames are allowed to be sent by the sender. Receiver on the other side also maintains a receiving window that corresponds to the set of frames which are to be accepted or which are permitted to be accepted. Now, in the case of the sliding window, the sequence numbers within the sender's window represent the frames that either have been sent or can be sent but are not yet been acknowledged. So the sliding window, once again, let me tell you, may be representing the frames that have been sent already, or it can also represent the frames that can be sent or that have been sent but not yet been acknowledged. So whenever a new packet arrives from the network layer, it is given a next, that is the highest sequence number. If, for example, 1 has already been sent, the next frame will be getting 2 and so on. Now once a frame is sent, the upper edge of the window is advanced by 1. We'll see with the diagram next. When acknowledgement arrives for the same frame, the lower edge is advanced by 1. This is how the protocol maintains a list of unacknowledged frames. Effectively, the protocol needs to check which of the frames have been acknowledged and which have not yet been. So this is a diagram that depicts how the protocol, or actually the sliding window, is used. Now this is the sender and this side is the receiver, where the figure A is in first column and figure B, they are depicting two different things. This is a sliding window of size 1. That means only one frame can be there into the sliding window. Once again, the sliding window will be checking one single frame at a time. That means the sliding window of size 1 with a 3-bit sequence number. That means the sequence number can have 3 bits. That means it can go from, let us say, 0 to 7. So it can advance from 0 through 7. So figure A depicts the initial situation where the sender has not yet transmitted the first frame, but the receiver is expecting frame number 0. That's why the window for the receiver has been open and it is waiting for the frame number 0. Figure B, on the other hand, after the first frame has been sent by the sender, so that the sender has now opened its window, indicating frame number 0 has been sent but not yet been acknowledged. The frame has not yet been received at the receiver. That's why the receiver is still waiting for the frame. This is indicated by the open window here, the receiving window. Now in this diagram, which is C and these diagrams C and D, they indicate, the figure C indicates after the first frame has been received, what happens. Now as you can see, the sender has opened the window for frame number 0. That means once again it is waiting for the acknowledgement of the 0th frame. At this time, the figure C is indicating that receiver has received frame number 0. That's why the receiver has simply advanced the receiving window now to indicate it is now expecting frame number 1 from the sender. So the window has been taken next. Figure D now indicates the scenario after the first acknowledgement has been received by the sender. So when the receiver received that 0th frame, it sent back the acknowledgement for that, and somewhere the sender received that acknowledgement. That's why the window is now closed. The other part of that window is now closed, and now the situation is as can be seen here. The receiver is now waiting for the frame number 1. So basically, to repeat, the scenario is something like this. If you are getting the kind of animation, after sending the first frame, sender will open the window and it will eventually be received. So previously receiver was waiting for 0. Now it is waiting for, after the reception of the 0th frame, it is now waiting for first, I mean the one number of frame number 1. In the case of the next diagram, you can see when the sender receives the acknowledgement, previously it was open here, And when the acknowledgement for the 0th frame was received, the window is now closed. This is indicated here like this. So this is how the sliding window always represents at the sender the frames that are yet to be acknowledged, the frames that have been sent but are yet to be acknowledged. Whereas in the case of receiver window or receiving window, it always indicates the frames which are expected to be received or by the receiver. Now in the case of 1-bit sliding window protocol, that 1 bit means the window size is 1. It can always be checking for only one single frame. And as it is only checking for one frame, it corresponds to the stop and wait protocol. The frame will be sent, and until its acknowledgement is received, next frames cannot be sent. That's why it sends, stops, and waits for the acknowledgement. That's why stop and wait. Now this is indicated by the actual algorithm of this protocol, 1-bit sliding window protocol. Here the protocol 4 is 1-bit sliding window protocol, where we define the max underscore sequence to be equal to 1. Next we define the event type as an enum with possible values of frame underscore arrival, checksum underscore error, or timeout, where the definition of the protocol now defines sequence numbers next frame to send. Sequence number frame underscore expected. Two frames have been defined, one is R and one is S. Buffer is a packet type and event underscore type. That means one event is a variable which is of type event underscore type. That means once again that can have any of these possible values. So the next frame to send is initialized with 0 along with the frame expected as 0 as well. So these are the variables that will indicate which frame is to be sent next by the sender and which frame is being expected by the receiver. Now, at the initial go, a packet will be accepted from the network layer that will be stored into buffer, and that part will be stored into the info variable of the frame S, whereas the sequence number will be given as next frame to send, which was initialized to 0, whereas the acknowledgement is a toggle between 1 and 0 that is made about by 1 minus frame underscore expected. If frame expected was 0, it is 1 minus 0, that means 1. If frame expected is now 1, it is 1 minus 1, that means 0. So acknowledgement will always toggle between 1 and 0. Similarly, the next frame to send will also be toggling between 1 and 0. So once the frame is ready, it will be then delivered to the physical layer, and a timer for that frame for the corresponding sequence number will be started. Now in an infinite loop, there will be a wait for the event. So three possible events are there: frame arrival, checksum error, or timeout, as we have seen previously. So if the event is equal to frame arrival, that means a successful frame arrival is there. Frame arrives without any error. So in that case, it will be accepted from the physical layer in a frame variable R, and now the receiver has to check whether that frame or the sequence number of the frame is in the sliding window or the receiver sliding window. So if r dot sequence number is equal to frame underscore expected, that sequence number happens to be in the receiver sliding window, then it will be delivered to, or the packet from that frame will be delivered to the network layer, and the frame expected will be incremented. So that means if the 0th frame was received successfully, next frame with number 1 will be expected next. Now, if the acknowledgement is equal to next frame to send, that means uh, the acknowledgement has been correctly received, which is equal to if the sequence number for the next frame to send was matching with the acknowledgement. That means the acknowledgement has been correctly received for the previous frame. So it has to stop the timer for that acknowledgement number, and it can now accept a next packet from the network layer and increment next frame to send. That means now the recently accepted packet can be sent as a new frame. So after that, that packet will be attached to, as we have seen previously, the info part of the frame. Next sequence number will be given to that next frame to send, and s dot acknowledgement, that means once again acknowledgement will be 1 minus frame expected, and now the newly formed frame will be given to physical layer, and a timer for that will be started. Up till this, we have seen two different functions, one for sender and one for receiver. Here, the same function is working for both sender and receiver. There is no separate functions given here. They are working parallelly. We'll now examine the scenarios, one which is the normal case and one in figure B, the abnormal case. In the case when either of A or B, the sender, I mean the one of the both parties communicating, if one of them sends a frame, I mean there is no simultaneous transmission, then the normal communication can happen. If both the parties start sending the frames at the same time, there could have been some problems. We'll see with the discussion here. Now imagine A means the first party, sends a frame with this notation, where the notation means the first entity is the sequence number of the frame. After comma, the second entity is the acknowledgement of the previously received frame, and the third quantity is the packet number within that frame. And here the asterisk will indicate where a network layer accepts a packet. When means where there is asterisk, there only the network layer is given the packet. Otherwise, the frame will be discarded. So we'll start. A sends the first frame 0, that means the sequence number of the first frame. 1, that is the indicating the frame acknowledgement number, and A0, which is the packet number. Now after some time, B gets the same thing, the frame with the same numbers 0, 1 and A0. As it is a new packet, it is given to network layer. That's why this is the asterisk. Now after that, B sends a frame with sequence number 0, its first frame. The acknowledgement now indicates it has received a frame with sequence number 0 from A. That's why this sequence number is 0 as the acknowledgement, and B0, that means the first packet from side B. Now after some time, it gets to A. So A gets the same thing, 0, 0, B0. That's why it is given to network layer, its network layer. After that, A sends a next frame, new frame with next sequence number after 0, 1, and it has just received a frame with sequence number 0 from B. That's why it is given as the acknowledgement field. and the next packet is there. That's why the next number A1. Now that is arriving at B, and as it has not already received, that's why A1, the new frame with sequence number 1, B has simultaneously got the acknowledgement for the previously sent frame, and A1 is the newly received thing. That means the sequence number 1 has not already been received. That's why the contents, that is A1, is given to network layer, and the same things go on. The point here is that you can see that most of the frames are accepted by the network layer. So effectively, there are no duplicate frames and no wastage of bandwidth. Now the scenario when both the parties A and B simultaneously start sending the frames, there may be some problems with C. So A sends a frame with 0, 1, A0. Simultaneously, B also sends a frame with 0, 1, B0. Now their timers are of different lengths. That's why one may be elapsing prior to the second one. So we'll see sequentially. A sends 0, 1, A0, B sends 0, 1, B0. So the next event is B gets the frame that has just been sent by A, 0, 1, A0. So it is the frame which is not already received. That's why the network layer is given the packet with value A0. Now after that, B sends 0, 0, B0, because the 0, it retransmits the first frame. Why? Because it has not yet received the acknowledgement for that. The first frame sent 0, but it has just got 0, 1, A0, which is a valid frame. That's why its acknowledgement is given here, and the previous content B0 is repeated. So it is sent to A. Meanwhile, A gets the first frame sent by B, which is 0, 1, B0. Now, as it was the first frame received from B to A, it is given to network layer. That's why the asterisk here. Now to indicate the receipt of the zeroth sequence number, it is given as the acknowledgement in the new uh, uh, frame, but as it was not, I mean, it has not yet received the acknowledgement for the first frame sent. It is rather simply retransmitting the first content in the next frame. So the sequence number is once again 0, but only thing is that it has just received the frame number 0 from B. That's why its sequence number has changed, acknowledgement number has changed to match the sequence number of the frame just received and the previous content of A0, because this frame has not yet been acknowledged. Once again, the transmission is there, retransmission. Now here, that frame is just received by B. B gets 0, 0, A0, which was just sent. But as a frame with sequence number 0 was already received, it is discarded, and that's why this frame is not given to the network layer. Whereas the only thing is that it has got the acknowledgement for the frame which was sent here. And that's why B now sends a new, goes to the network layer, accepts a new packet and forms a new frame out of it, gives a new sequence number, acknowledge the previously received frame with 0, and a new packet as B1 is contained into the frame, and it is now sent. And these things continue. The point here is that most of the times, or at least half of the time, you can see that the packets are not given to network layer because they are just the retransmissions. So this is the problem when both the parties A and B start to send the frames at the same time. Now, the assumption that you are taken in all the protocols so far is that the time required for transmission and reception of the acknowledgement packets is negligibly small. So that we have just considered that it will not take much of the time or considerable time for the transmission or reception of the acknowledgements. Now, that is not practically possible because there can be lengthy routes. A and B can be far apart, and the acknowledgement, however small they can be, they may take some time, and that's why these assumptions will be most of the times not true. And there'll be a round trip time for the packet sent from A to B and its corresponding acknowledgement received back to A. That is what is called as the round trip time. This particular round trip time can have important implications on the efficiency of the communication and the bandwidth utilization. We'll see this with one example. Imagine one arbitrary satellite channel with 50 kbps bandwidth. That means 50,000 bits per second can be transmitted. Here the round trip propagation delay is 500 milliseconds. That means it will take 250 milliseconds for one way transmission. Now, the previous 1-bit sliding window protocol will be used here to send 1000 bit frames via satellite, this particular channel. Now, for the initial go, that means time was 0, the sender starts the first frame here. After 20 milliseconds, means if it is 50 kbps channel, to transmit 1000 bits, it will take 20 milliseconds. The first frame has been completely sent after 20 milliseconds. After 40 milliseconds, the next frame or the second frame has been sent. So after 270 milliseconds, the frame has fully arrived at the satellite, which is here. Why 270 milliseconds? Because the propagation delay was 250 milliseconds and it took 20 milliseconds to completely transfer one single frame. That means if had that been only a 1-bit frame, that would have taken 250 milliseconds. But it took 20 milliseconds to transfer 1000 bit. That's why those 20 milliseconds were added to that, and that's why the total time was 270 milliseconds. That is very important to be understood. Now, after 270 milliseconds, the complete frame has been received by the satellite. And let us say, for example, it will take, obviously, because the round trip time of propagation delay is 500 milliseconds. So the next 250 milliseconds will be required for the acknowledgement frame to be received at the sender. So 270 plus 250, that means 520 milliseconds. After 520 milliseconds, the acknowledgement has been received at the sender. Now, if you consider this total scenario of the total time, that is 520 milliseconds, for 500 milliseconds, or that means 96% of the total time, the sender did not do anything. That means the sender was blocked. And for the rest of the time, that means only 4% of the time, the sender was busy, and thus the sender utilized 4% of the available bandwidth. Now, the problem, what is the problem? Here the problem was that the sender was not allowed to transmit the second frame or any other frame before the acknowledgement for the first frame was received. If you relax this condition, we may be able to achieve significantly better throughput. Now, hence, the solution lies in allowing the sender to transmit some W frames before blocking. So rather than simply sending one and waiting for its acknowledgement, the sender is now allowed to transmit some particular W frames. And after sending the W, it will wait, it will rather be blocked. Now, as the W frames are being sent one after the other, the corresponding acknowledgement will be gradually received at the sender before the window becomes full. So the most important issue here is to identify what could be the actual size of W, which closely resembles or that is dependent on the number of frames to fit inside the channel. That calculation of W requires calculating how many frames will fit inside the channel. And to know that, we need to calculate the capacity of the channel, which is given by the bandwidth of the channel in bits per second, which is B, multiplied by one-way transit time, that is D. That comes out to be the bandwidth delay product of the communication channel given by BD. Now it has been calculated that the proper value of W should be made equal to 2BD plus 1. Now we have already seen that the bandwidth delay product is BD. So 2BD, that means double the bandwidth delay product plus 1. That 2BD gives the number of frames that can be waiting, or for those many frames the center will not block, and plus 1 basically indicates the frame will be, or the acknowledgement will be transmitted when the frame has completely been, or one single frame has completely been received by the receiver. That's why that plus 1. For the acknowledgement to start, that first frame has to be received by the receiver. That's why the value of W is equal to 2BD plus 1. We'll know this with one example. Now, as previous, the channel is with bandwidth of 50 kbps, one-way transit time of 250 milliseconds, and the corresponding bandwidth delay product is 50 kbps into 250 milliseconds, which is 12.5 kbps, kilobits, sorry. Or we can also calculate the number of frames here. That means 12.5 frames of 1000 bits, because it is 12.5 kilobits. Now 12.5 is BD, and that's why 2BD is 25 plus 1, 26. So the value for W comes out to be 26, or 26 frames. Now with this, at the initial time, that is 0, or T is equal to 0, the sender sends a first frame and subsequent frames after every 20 milliseconds. At the time T, which is 520 milliseconds, as we have seen previously, the acknowledgement for the first frame has been received, whereas at the same time, the 26 frames have already been transmitted in the same time, 520 milliseconds, because it took 20 milliseconds for one frame, so 520 milliseconds for 26 frames. And the beauty here is that in the same time, 520 milliseconds, the sender is it is getting, or it has started getting, the acknowledgements as well for the corresponding 26 frames. And thereafter, acknowledgements will arrive every 20 milliseconds. In short, the sender is not waiting for accepting or receiving the acknowledgement here. It is not wasting the bandwidth. This is how the W, whenever it is made to be equal to 2BD plus 1, the bandwidth utilization is optimum. Now, here the 26 unacknowledged frames will always be outstanding in any case, The first 26 frames have been sent, the corresponding acknowledgements are being received. So there will be 25 or 26 unacknowledged frames always in the channel, and that's why the sender is not waiting ever. I mean, not blocked or not. There is no situation that the channel is not transmitting any data. Hence, the sender's maximum window size here, as you have just seen, comes out to be 26 frames. Now, for smaller window size, if the W is made smaller than 26, obviously the utilization of the link will be less than 100%. Now, the upper bound of the link utilization, how much can be the link utilization? We can make it or calculate it to be, the link utilization will always be less than or equal to a ratio which is the actual window size upon 1 plus 2 BD. Now we know that if W is made optimum, for example 26 here, 1 plus 2 BD will always in that case 26. So 26 upon 26 it will be 1. That is the optimum channel utilization. If W is made lesser than 26, that means the window size is made lesser than that, the link utilization also will be decreasing. Now here we are not considering any frame processing time, as the frames are being transmitted and then eventually they are received at the data link layer of the receiver. The receiver can at the same time get all the frame without wasting any processing time, wasting for any processing time. Alternatively, we are also treating the acknowledgement frames having zero length. Now, as can be seen from the same equation, the bandwidth delay product and the calculation of W, large bandwidth delay product requires a large window. W will be large if BD, that is the bandwidth delay product, is large. Now, if W is equal to 1 in the case of stop and wait protocol, even though there is even 1 frame's worth of propagation delay, the efficiency will always be less than 50%, because for every frame sent, it has to get the acknowledgement back. It has to wait for that acknowledgement, where that time will be equal to the propagation time delay time D. Now, in the case of the previous case that we have seen, a technique called as pipelining can be used, where the number of frames which is greater than 1 are sent immediately without waiting for first frame's acknowledgement to be received. That is what is called as pipelining. Multiple frames are being sent simultaneously. Now there can be a scenario when any one of the set of the frames which are just been sent can be in error. Now if that frame happens to be a middle frame or a frame at the end, or maybe a frame at the beginning, what happens to the frames which are sent next to it? That is the issue. So there are two ways of tackling that issue. The first issue, or the first way, is called as go back in, or the protocol go back in. Basically, here when one such frame is received in error of the set, the rest of the frames, even though they are received without any error, they are discarded. Rather, they are made to go back to the sender, and that's why the name go back in. Here, as you can see, this is the timeout interval of the sender. These these are the sequence number of the frames being transmitted. This is the sender side and this is the receiver side. So frame number 0 and 1 are correctly received at the receiver. Correspondingly, their acknowledgements are being sent back. They are also received at the sender after some time. But for frame number 2, it was received in error. and that's why its acknowledgement was not obviously sent back. So when the timer for that frame number 2 was elapsed and the acknowledgement for that frame number 2 was not received up till this time, the sender simply started sending all the frames right from that sequence number 2, 3, 4, etc. once again. Meanwhile, apart from frame number 2, rest of the frames in the sender's window, that means 3, 4, 5, 6, 7, and 8, they were correctly received. Even though as frame number 2 was not received correctly, the rest of the frames up till 8, even though they were correctly received, they were simply be discarded by the data link layer of the receiver. And that's why the sender had to send all the way from 2, 3, 4 up till 8 once again. So now the frame number 2 was received at the receiver, and the corresponding acknowledgements have been sent back. So this is what is called as go back N protocol. Here the effective send receiver's window size comes out to be 1, and one frame was received in error. You have seen what happened here. The second strategy is not to discard the rest of the frames but to buffer them, and that is what is called as selective repeat. Only the frame which was received in error, that will be retransmitted. Here, just to narrate the scenario, as was there in the first case, the frame number 0 and 1 were successfully received. Unfortunately, frame number 2 was not received successfully. Some error was there. So acknowledgements for a frame number 0 and 1 were sent back. As frame number 2 was not received, but there were some buffers for the rest of the frames, for example, frame number 3, 4, 5, etc. They were simply buffered there. And when the next frame was received, a negative acknowledgement for the previous sequence number, that is frame number 2, was sent back. And then no such acknowledgements were given for frame number 3, 4, and 5. When that negative acknowledgement was received at the sender came to know that the receiver did not receive frame number 2, and that's why it retransmitted the frame number 2 to the receiver. When it was received, meanwhile, frame number 3, 4, and 5 were actually received successfully at the receiver, and they were buffered there. And then the receiver was having all the way from 0 to 5 all the frames, and that's why receiver simply sent back a cumulative acknowledgement only for frame number 5. Receiver did not send acknowledgement for 3, 4. It simply sent an acknowledgement for the last frame in sequence received correctly, that was 5. When it was received at the sender came to know that the receiver has received all the way the frame numbers from 0 through 5 at the these frames have been received at the receiver. So meanwhile, it has already started sending next frames, which is 6, 7, 8, etc. So this is the meaning of selective repeat, wherein only the frame which is not received by the receiver will only be transmitted. Here the effective window size of the receiver is not 1, it is larger, and that's why it could receive multiple frames, whereas the previous frame may have been received in error. Now, as we have just seen, the cumulative acknowledgement, when an acknowledgement comes in for frame number n at the sender back, it assumes that the frames n-1, n-2, or all the previous frames have been correctly received, and that means they are automatically acknowledged. Now, as you have seen previously, the go back in protocol basically simultaneously, starts sending all the way frames. In the case of this example, 0 through 8, they were sent one after the other without waiting for the first frame. That means there'll be multiple outstanding frames, and that's why logically multiple timers are also needed, one per outstanding frame. Each frame times out independently of all the other ones, and that's why they'll be having their own timers. And the pending timeouts, they form what is called as a linked list with each of the node of that containing the following values. The first is number of clock ticks until the timer expires, the sequence number of the frame for which the timer is started, and the third is the pointer to the next node, as can be seen in this diagram, where the time is shown, the real time is shown here with milliseconds. The first node indicates the ticks to go are 5. 1 is the sequence number of the frame for which the timer has been started, and the third field is the pointer to the next node, and so on. So when 5 milliseconds have been elapsed, the situation is shown in figure B. Now, as the 5 milliseconds have been elapsed, the pointer is increased to node 2 and the first node is taken out. Now, as you have seen, the go back N protocol will work well if there were no errors or there are very small number of errors. If the channel is noisy or there are multiple errors or frequent errors, the go back N protocol, as it has to send back the correctly received frames as well, it wastes lots of bandwidth for retransmission of the frames. The next protocol, which is a selective repeat protocol, allows the receiver to accept and buffer the frames following a damaged or a lost one, as we have seen in the previous case. Here, the sender and receiver maintain a window of outstanding and acceptable sequence number respectively. Sender's window will start with 0 and it will grow to some predefined maximum number. Similarly, for receiver, it is always fixed in size, as you have seen in the previous example. That number is a predetermined maximum number. It has also got some buffers reserved for each sequence number within its fixed window. It has also got a bit that tells whether the buffer is full or empty. Now, whenever the frame arrives, the receiver simply does the following. It checks whether the frame sequence number falls within the fixed window in the receiver's window. If that falls within that window and that sequence number has not already been received, that frame will be stored. So it does so without regard if the frame contains the next packet expected by the network layer or not. Now, this frame is going to be kept until the lower number of frames have been delivered to the network layer in the correct order. As we have seen in the previous case, the frame number 2 was not received, even though frame number 3, 4, and 5 were saved. So, the frame number 3, 4, 5 will be saved until frame number 2 has been received, and then they will be given to network layer in the correct order. Now, that means the frames can be received in a non-sequential way. Now, this introduces a further constraints on frame sequence numbers as compared to the protocols that simply accepts sequential frames. Now, we will consider this with one example with 3-bit sequence number. As the bits are 3, there can be sequence number going from 0 to 7. So 7 frames are permitted to be sent by the transmitter before it is required to wait or block. Now the window size restriction basically here is max sequence plus 1 upon 2. That means it must be at most half the range of the sequence numbers. Now why this is, we'll see with one actual example. As can be seen here in the diagram, the first row is the sender and the second row is the receiver. The sender's window size is having 7, as it was 3-bit, 0 through 6. Corresponding, the receiver was also waiting for the 7 frames, 0 through 6. Now, whenever 0 through 6 frames were sent by the sender and they were eventually be received at the receiver then send back the acknowledgement for those 7 frames. But this is where the problem striked, and the acknowledgements, all the acknowledgements have been lost in the reverse way. They couldn't get back to the sender. So the receiver was simply waiting for, rather here at this situation, the sender is not known whether, the sender is not sure, sender is not acknowledgement, has got acknowledgement for frame number 0 through 6. That's why it is always be transmitting the same frames 0 through 6, this particular part. But for the receiver, it has correctly received the first set of 0 through 6. It has acknowledged, and that's why it has changed or advanced its window now containing 7, 0, 1, 2, 3, 4, 5. Whereas the sender has not got the acknowledgement for the sequence number 0, 1, 2, 3, 4, 5, 6. So the sender will time out and it will eventually send the frame number 0 once again. Coincidentally, that frame number 0, as the logic indicates, happens to fall within the receiver's window. So from the sender's context, it has sent once again the previous frame number 0. From the receiver's context, it has received a new frame which coincidentally falls within the receiver's window. That is the problem. And as that has received the frame with sequence number 0, which was already there with that, so it will rather acknowledge that with the last successful sequence number received 6 as the acknowledgement number, and that comes at the sender, and that's why the sender wrongly concludes that all the way 0 through 6 are the frames have been received, and that's why the next frame, which is 7, will be sent. Now for that 7, that also happens to be with the receiver's window, that's why that will be accepted, and then the sender will once again transmit 0, 1, 2, 3, 4, 5, etc. But now the problem is that 0 through 5 have already been there in the receiver's sliding window. That's why these will simply be discarded and the previous frames will be sent along with sequence number 7, so that the receiver's network layer will be getting wrong packets. In short, the problem here that the sequence numbers or the sliding window range or the size of the sliding window was not chosen properly. When it was advanced, it happened to collide with the same sequence numbers which were there with the previous sliding window. And that's why if the frames have been acknowledged, the next successful retransmissions will be taken as duplicate. That is the problem. Ultimately, the proper value has to be max sequence plus 1 upon 2. That is given in figure number C and D. In the case of figure number C, the out of the total 8 sequence numbers, the window is now chosen to be 7 plus 1 upon 2. That means 4. 0, 1, 2, 3 is the situation in the initial case, as it can be seen here. Similarly, the receiver is also waiting for 0, 1, 2, 3. So whenever all the frames from 0 through 3 have been sent and they have been correctly received, the receiver will advance its window to indicate for the next 4 frames 4, 5, 6, 7. Here they do not collide with the sender's window or the previous values 0, 1, 2, 3, and that's how, even though the frames come any frames come from 0, 1, 2, 3, they will not be accepted because they do not fall within the acceptable receiving window. That's why there is no problem of sending the previous copies to the network layer. Only when the sequence number 4, 5, 6, 7 come, then only the packets for the corresponding frames will be sent to the network layer. So here we have seen the sliding window protocol, 1-bit sliding window protocol, the go back N and selective repeat. All the resources for this will be available to you with this blog that is being displayed here, vishalparkar.blogspot.com. You can see all my previous videos at this YouTube channel, Vishal Parkar. Thank you.